Okay, still on page 408, number 3, Keno. So, 4-spot Keno is you pick 4 numbers from 1 to 80, and then they draw 20 random numbers. And if you match any of your numbers, you win. So, in other words, right here, 0 numbers, you don't win anything. 1 number, you still don't win anything. But if you match 2 of your numbers out of the 4 that you picked, you get your money back. You really need to get 3 numbers, and you get $3. But if you match all 4 numbers, what do you get? It's like 126 bucks? No, it's $120. Okay. Now, they tell us the mean and the standard deviation, like that. Okay. So they ask you, what does this mean? What does this average mean? What does this standard deviation mean? Well, what it means is, for every time that you play this game for $1, you should expect to lose 30 cents on average. So you play it many, 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 many times. Sometimes you win, sometimes you lose. So in other words, let's just say you play this game 100 times in a row. What should you expect to end up with? Well, $70. You probably lose $30 of that $100. But there is a big swing, $6.58, because this is so large if you hit all 4. See, that's the thing about this game. You really want to get all 4 to get anything out of this thing. So, anyway, there you go. This is your average take, and this is how much it could vary high or low. Okay, I think we know that. So Jerry, this is letter B, he decides to place a single $5 bet. Okay, so what does that do to our average and standard deviation? Well, it multiplies them both by 5. And what do we get as an answer? And there it is. So that's kind of like, let's just say he bets $5 every time. His average take, he should lose about $1.50 on average. But there is a very big swing in case he does win that big money. $32 either way. Okay. So C is a little bit different. Who is it? It is Marla. So Marla is going to bet 5 individual $1 bets. So that's letter C. So how does that work? Well, the new, let's call this the new average would be, what is her expected value? 70 cents, right? And we add them all together 5 times. 70 cents, 70 cents, 70 cents, 70 cents. And we add them all together. And that's actually just the same thing as times 5, right? So her expected value should still be $3.50. But what about the standard deviation? So the standard deviation for Marla would be, we would have to take the, how much was it? $6.58. $6.58, square it, plus $6.58. Right, we're going to do this 5 times, and square it, $6.58, and so on and so forth, and square it. Okay, 5 times. And then take the square root. Okay. One, two, three, four. Oh, I always run out of room. Okay. $6.58, and square it like that. And take the square root of all of this stuff. So, what does that give us? The answer is $14.71. So here it is, $14.71. So in other words, for these two people, who was it again? Marla and Jerry. Jerry is placing a one $5 bet, but his standard deviation is big, so he plays one time and has a chance to win big. Marla, on the other hand, is playing 5 times, which means that her risk is lower here. Okay, so she doesn't have a chance to win quite as much based on the standard deviation, or at least that's where the odds are. So there's that. And then letter D is, which gambler would they rather have in the casino? So based on the casino's interest, they would probably rather have Marla because it decreases their risk of paying out. Okay? So, like the insurance company, we want to have a lower standard deviation of paying out those big wins or benefits in insurance. So, Marla, lower standard deviation, lower risk. Okay, there you go. So here we go. We have a machine that is screwing caps onto these oil containers. So torque is that twisting. The harder you can twist, the more torque you have. So if you twist too hard, it's going to snap the cap. So they give us some information. Let's see. The torque, right? That's the twisting force, has a mean of 7 and a standard deviation of 0.9 inch-pounds. And then the caps, so the cap strength right here is, they have 10, a strength of 10, and standard deviation of 1.2. So that makes sense to me because the caps have to be stronger than the torque, otherwise they would all break. Okay, so in other words, if this torquing machine goes above 10 pounds, it's going to snap the cap in half and break it. Okay, so let's look at letter A. Letter A says, explain why it is reasonable to assume that the cap strength and the torque strength applied to the machine are independent. Well, they should be independent because they're totally different machines that do each thing. There's the twisting on machine and then the machine that makes the caps. Different machines. Now let's look at letter B. So what we're going to do is we're going to look at a new mean and standard deviation, basically the difference of the cap strength minus the torque strength. Okay, and do the mean and standard deviation. Well, let's do this. We'll just call it the mean of D, which is cap strength is 10 and the torque strength is 7 on average. So we're going to have a new mean of 3 when we subtract those two. Then the standard deviation, let's see, that might be a little bit different. So what do we got to do? Oh, we got to square them and add them and take the square root. So let me do that. So there it is. And don't forget, I've said this many times, always add the standard deviations. Even though we're subtracting them, we always add the standard deviations. So here's our new situation right there. So is that all of B? Yes. And then what does it say for C? It says, what is the probability that a cap will break while being fastened by a machine? Show your work. Okay, so this is going to be a z-score. So here we go. So here's our z-score. Here's our new average and our new standard deviation. But we want to say, when will it break? Well, if we look at this, if the torque is stronger than the cap, it'll break. So anyway, if they're equal, it should be okay. But basically, if we're going to get a negative number, probably 0, anything less than 0, right? If we get a negative number, this one is bigger than this one, and it snaps that cap. So what do we put for here? We're going to say, well, we're interested in 0. So it's going to be 0 and less, meaning this number is bigger than this number. Okay, that's all right. Let's see what that z-score is. Well, Actually, just do it in your head, right? It's going to be -2. -2. So we're -2 standard deviations below the mean. So what do we do with that? Normal CDF. Okay. And we get that. Now, do we subtract it from 1? No, not this time, because we want to know all of the numbers that are 0 or less over here. And that says, well, approximately about 2% of the caps are going to snap in this situation. Okay, I'm going to stop there and post this thing. Here we go.